Hello everyone, in this video we will understand what is Newton-Raphson method. Quickly starting with the definition, let x naught be an approximation to the root of the equation f of x equals to 0, and if x1 whose value is x naught plus h be the exact root of f of x equals to 0, it means function value at the point x1 should be 0, which is equals to f of x naught plus h. Now expanding f of x naught plus h by Taylor series, we get f of x naught plus h is equals to f of x naught plus h times f dash x naught plus h square by 2 factorial into f double derivative at point x naught plus so on to this value is equals to 0. Since the value of h is small and we can neglect h square and the higher power of h, we get that f of x naught plus h times f dash x naught is equals to 0. From here we can find the value of h as minus of f of x naught divided by f dash of x naught. Therefore, a closer approximation to the root is given by x1 is equals to x naught minus f of x naught divided by f dash x naught. Similarly, starting with x1, a better approximation x2 is given by x2 is equals to x1 minus f of x1 divided by f dash of x1. In general, xn plus 1 is equals to xn minus f of xn divided by f dash of xn, where n is equals to 0, 1, 2 and so on, which is known as the Newton-Raphson formula or Newton's iteration formula. Newton's method or Newton-Raphson method is one of the most powerful and well-known numerical method for solving root finding problem. Now, let us see its geometrical interpretation. Let this be the graph of y is equals to f of x, and it cuts the x-axis at the point P, let us say. So we can say that P is the root of my given equation y is equals to f of x. Let us suppose x naught be my initial approximation to the root. Then its corresponding value of y be p naught. Drawing the tangent at that point which cuts the x-axis at the point x1. Now we have moved from the initial approximation x naught to x1, and it cuts f of x at point p1. Again drawing the tangent at that point which cuts the x-axis at the point x2, and its corresponding point at the equation y be p2. Again drawing the tangent and continuing this process, we will get a sequence of points xn which will converge to the point P. So this is how the Newton-Raphson method works. We can also note that let f be my twice continuously differentiable function over the closed interval AB, and if there exists a point P from the interval AB is such that f of P is equals to 0 and f dash P is not equals to 0, then there exists a delta greater than 0 such that Newton-Raphson method generates a sequence xn converging to P for any initial approximation P naught from the interval P minus delta to P plus delta. Even if Newton-Raphson method is powerful, it still holds some limitations, which is the proper choice of initial approximation is very important in this method. This method is very sensitive to the initial approximation, If the initial approximation is chosen sufficiently close to the root, then the method will converge very fast. But if the initial approximation is not sufficiently close, then the procedure may fall in an endless loop. Let us understand this thing with the help of a graph. Let this be the graph of y is equals to f of x. Here p is my root of the given equation. When we take the initial approximation as x naught, which is close to the point p, or we can say which is close to the given root, then the method will converge very fast. But the case when we take the initial approximation as x2, then the corresponding point, then the tangent at the point p naught is parallel to the x-axis. So the slope of tangent at this point will become 0. So this method will diverge. And when we take the initial approximation as x3, the corresponding point bp3, and when we will draw the tangent which will cut the axis at the point x4, and the corresponding point be p4, and when we will draw the tangent at the point p4, it will again intersect at the point x3. So this method will fall into an endless loop. From here we can see the importance of selecting the initial approximation for Newton-Raphson method. Now let us try to understand this Newton method with the help of an example. In this example, the initial approximation is not given, so firstly we have to find out where the root will lie. For that we are given f of x is equals to x cube plus x square plus 3x plus 4 equals to 0, implies the derivative of this function with respect to x is 3x square plus 2x plus 3. Now let x is equals to minus 2 implies f of minus 2 be minus 2 to the power 3 plus minus 2 to the power 2 plus 3 into minus 2 plus 4, whose value is minus 6, which is less than 0. And for value of x as minus 1, function value becomes one, which is positive. Since the intermediate value property is satisfied for the value of x is equals to minus 2 and minus 1, so a real root of given equation lies between minus 2 and minus 1. Since we have understood that initial approximation in Newton's method is very crucial, we have to take the initial approximation which is near to 0. And from here we can notice that f of minus 1 is near to 0, then f of minus 2. So taking initial approximation as minus 1. For the iteration 1, x1 is equals to x0 minus f of x0 divided by f dash of x0. Substituting the values, we get minus 1 whole divided by 3 into minus 1 square plus 2 into minus 1 plus 3, whose value becomes minus 1.25. Moving to the second iteration, the second approximation be x2 is equals to x1 minus f of x1 divided by f dash of x1, and its value becomes minus 1.22289. For the third iteration, the value of x3 becomes x2 minus f of x2 upon f dash of x2, and its value becomes minus 1.22249. For the next iteration, x4 becomes minus 1.22248. From the third and fourth iteration, it is clear that there is no change in successive approximations to the root up to first 4 decimal places. So, a real root of given equation is x is equals to minus 1.2224, correct up to 4 decimal places. Let us do one more question, which says to find the root of the equation x into sin x plus cos x equals to 0. The given equation is x into sin x plus cos x equals to 0. Let f of x be x into sin x plus cos x, implies its derivative with respect to x becomes x into cos x plus sin x minus sin x, which is equals to x into cos x. Since we have to find out where the intermediate value property will hold, so letting x is equals to 2.5, the function value at 2.5 be 2.5 into sine of 2.5 plus cos of 2.5, which is equals to 0.6950. And for the value of x equals to 3, function value be 3 into sine 3 plus cos 3, which is equals to minus of 0.566. So a real root of given equation lies between 2.5 and 3. Also, the function value at 3 is nearer to 0 than function value at 2.5. So, take initial approximation x0 to the root as 3. Starting the iteration, the first approximation be x0 minus f of x0 divided by f dash x0, which is equals to 3 minus 3 into sin 3 plus cos 3 divided by 3 into cos 3, whose value be 2.8092. For the second iteration, x2 be x1 minus f of x1 by f dash of x1, whose value is 2.7984. For the third approximation, x3 be x0 minus f of x2 by f dash of x2, which be 2.7984. From the second and third iteration, we can see that there is no change in the successive approximation to the root. So, a real root of given equation be x is equals to 2.7984. I hope you have made an understanding how you have to proceed with the questions based on Newton-Raphson method. Here are some practice questions for you. The first question I have given you is already been discussed using bisection method. You have to solve this question with the help of Newton method and compare how many iterations it took in bisection method and in Newton-Raphson method. You can also perform this question using fixed point iteration method and compare the number of iterations. Practice these questions and let me know if you still have any doubts in the comment sections. Keep learning.